Okay, my friends, a solar shocker du jour today. This is all coming up now is going to be the solar eclipse very soon. And as you can see, we had 1 day ago, solar eclipse, 4 hours ago, 3 hours ago, 2 hours ago. This is going to be a big thing, and it's a big deal. And why is it a big deal? Because they're going to try to study the solar corona. And what is the solar corona? Well, let's look into it. All right, here's the issue. The sun's surface is 10,000, and out here, where it scrubs, and you see all these little negatives, those are the ions. And where it's out here, it's millions of degrees. And because everywhere else out here is saturated with ions too, because they're nothing more than light. Light just keeps going. It doesn't just stop there. It just keeps going. So from everywhere in the whole universe, it's just saturated with particles. And everybody knows this. It's not a mystery. We know that it's saturated with particles. We've known this for a very long time. So as we spin through all those particles, we scrub through that. And we create, first of all, huge magnetic fields. Secondly, a lot of heat. Obviously, it's millions of degrees out here as we plow through, and we're scrubbing through the universe on an arm of the Milky Way, spinning around and around and around, and whatever we have to plow through, we've got to plow through it. And when we plow through it, it looks like we're plowing through just like this. We're on that arm of the Milky Way, zoom. The sun is spinning, we're spinning behind the sun trying to catch up with it. That's gravity. And the sun has a lot of gravity, and the gravity is the dark matter. And the dark matter is attached to the white matter. There's no difference. Well, I mean, there's 100% opposites, but they are together as one. And that's dipole electron flood theory. It solves everything. It solves everything. And it works 100%. And I can show it. It's not only does it work, I can show it. Before we go any further, I want you to just be certain you understand. We're scrubbing through space just as the sun is scrubbing through space. The sun is emitting a ton of particles. We're not emitting particles like the sun is, so we don't have that millions of degrees out there, but we still got a pretty hell of a good temperature increase as you go out. The sun is a different category. It's just sending all of these particles radiating out to engage with the other particles it's got to plow through. Plus, its diameter is much bigger. And the reason we're increasing with the global warming is because of this. This scrub is getting hotter and hotter out here. And why? It's because of combustion. But it's not because it's just carbon. The carbon can't escape. It has nothing to do with that. It's because the envelope of our atmosphere is expanding. And as that envelope expands, it scrubs harder and harder. It just gets bigger and bigger. The more expansion, the harder the scrub. The harder the scrub, the more the heat. It's combustion, absolutely, no question. I agree with that 100%. The more combustion you have on the Earth, the bigger the envelope will be. It's just like you're blowing up a hot air balloon. It's exactly identical, same thing. No difference whatsoever. Okay, my friends, Exhibit A. This is basically outer space. It's not a vacuum whatsoever, absolutely not a vacuum, but it's not saturated with particles like our atmosphere is. But right here, you run into what's called the ionosphere. And this is the edge of the ionosphere where we spin through space and scrub against this zone. And right here, it's 1,500 degrees. And the northern lights show up here because there's all these charged particles. Ions are charged particles. Now underneath it goes to minus 80 degrees. So this is over, I think it's about 2,700 degrees, something like that, 2,500 degrees out here. And it's minus 80 degrees Celsius down here. That's over 100 below Fahrenheit. So you got a huge difference, which means it's a dipole. Hot and cold. That's exactly what it is. The white is hot, the black is cold. And then below that, it gets hot again. So it's hot, cold, hot. So the colder it gets here, the hotter it's going to get there. So the hotter it gets here, the colder it gets here, the colder it gets here, the hotter it gets here. And guess what? It's getting colder here. So So it's going to get hotter down here. They just don't understand it. They think it's getting colder here. That means something good. No, it means something bad, because it's a dipole. Hotter, colder. Colder, hotter. So don't forget, this is Earth. We're way out here with this huge temperature. Nobody talks about that. Now they're talking about the sun. Well, how come the sun's got a real high temperature way out on the outside edge of its atmosphere as well? Because it has an atmosphere just like us. But it's charged particles are radiating out through it. And when they hit the outer space of their corona, they get the same effect here. So for them, it goes from 10,000 to millions. For us, it goes from 100 and something up to 2,700 degrees. Nobody talks about that. So there's the sun behind the moon, total eclipse, bright spot, bright spot, bright spot. You see those 3 red spots? All right, you see them, those 3 red spots? And how they have fields surrounding them? But on the other side of the sun, you don't see that. That's because the sun is actually spinning this direction, so that means it's scrubbing harder. And this is the side that's sloughing back off. So it's going, the sun is going this direction, and it's spinning this direction. So this is the impact zone, and this is the slough off zone. This is the polarity, which is the north and south pole, basically. Anything that's a dipole and is spinning, it creates a north and a south pole. Light is dipoles. As I show a zillion times, I'll show it again right now. So what we have is, this is the interacting side of the sun spinning in this direction. And that's sloughing back off. But it's still radiating particles, like insanely number of particles. So way out, somewhere about out here, I would say it's about where the flux reconnects. Basically, maybe right about here would be where the corona is most intense. You're still going to have a hell of a lot of energy pouring off of these out here, but there's going to be a zone out here that'll be the most intense, and then it'll slack off. Or it could be way out here, I don't know. But I'm going to tell you right now, that thing is plowing through the atmosphere that's in front of it. And that atmosphere is not empty. It is saturated with particles. This is what we spin through. We're on the arm of one of these, on the galaxy here, or on the arm of some galaxy, which is called the Milky Way. I don't know what this is. This could, I don't know what it is. But it's spinning. They all spin. And as they spin, they tighten up. And they tighten up in the center, just like a wrench. And you can see it's pushing sort of this way, flapping the arms back. So it's coming in this direction, basically. And it pushes against everything just like we do. This is nothing more than just like, almost like a light particle. Everything has the same effect. And the closer you get to the center, the more energy you get. All right, this is from Fermilab, a long time ago. And they say they found the exact same particles we found, the black one with the glowy edge around it, and the white one, or red, whatever, blue, and that's exactly what we found. And here's our particles right here. That's what we found. These are the Fermilab ones I just showed you. And this is how they attach together. The black attaches to the white. So my theories are not theories. I can show and prove what I am saying. And we did experiments on light. Now they did experiments with big gigantic particles. So what they ended up seeing was this, just a big mess of stuff when they slammed these particles together. So what they did was they took particles like this. And they had them try to hit them head on. When they did, they got all stuff just looking just like that, just all crazy stuff. So every now and then, well, a lot, they would see one little bitty one, a black one. And they would see one little bitty one, a white one. And they'd say, ooh, those are the 2 smallest particles that exist. And I agree, because that's the muon, electron, neutrino. And that's what they showed here in their article. I'm going to go back to that in a second, because these are light. Because that's light from a red laser. This is light, and that's the photon. So these particles are coming off the sun as light to us. They're particles, they're not nothing. They are particles. And they are coming through the atmosphere towards us, spinning at us, literally, as light particles, which saturate space. All right, now here's the conclusion on these point particles, which this is the point particle. It can get big, it can get small, it has really no mass, and that has all the mass, literally all the mass, but it can't get any bigger, it can't get any smaller. It's what he calls it a fixed particle, and I agree. They don't get bigger, they don't get smaller, and they have no energy whatsoever other than attraction. So they're absolute zero. That's why it's so cold after you get, remember I showed you this? I don't want to lose you here. Remember this. Extremely hot out here and extremely cold down here. That's the nature of that white particle attached to the black particles. Basically, think of it along those lines. That's the dipole nature of it. All right, and this is the dipole nature I just showed you, the exact same particles right there. Now, he says that the extended particle has a fixed size. That's the black one. And has a fuzzy edge around it. Yes, that's the glowy part. Point-like particles are mathematical zero size. He's saying there's nothing to them. And I agree. They just have energy. And it says it has an extended field effect due to the field surrounding them. Now, then he talks about the quantum foam. Okay? Remember we talking about these two particles are light. Light is a particle. There's no question it's a particle. And it creates a wave because it's got a magnetic field surrounding it. I'll show you that carefully. Now, this brings us to the quantum foam. The quantum foam is right here. Empty space isn't empty. It's just not empty. There's no such thing as a vacuum in space. Totally, and I'll show you in just dizzying detail that that's so far from right. Now, these are all the particles that come through in a dizzying display of change. Well, what changes? Empty space experiences similar activity. It's not empty, that's why. There's all these light particles are floating around out there. And when they get slower and slower and slower, they end up being the cosmic microwave background, just particles. And as every other light particle comes through, bang, 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 bang. And that particle slows down, first of all. And secondly, the other ones get a little bit of a glow to them because they're impeding the forward motion in a dizzying display of change. Blink, 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 blink. When they hit head on or hit against each other's fields, they glow a little bit. And I can prove this as well. Everything I'm saying I can prove. So it says empty space, which isn't empty, experiences similar activity. Subatomic particles. Subatomic. That means smaller than an atom. That means these muons and electron neutrinos. These subatomic particles winking in and out of existence. Bang, 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 wink, 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 as they get hit by other things. There's a space between them. There's good-sized spaces between them. They're not right on top of each other like they are here in our atmosphere. Here, they're just right at one against the other. Out there, they're maybe this far apart. And there's space you could go through there, nothing would happen. But more often, they are still within a magnetic field of anything that's big in that area. Anything that's big is going to have a huge field, which I will show you. All right, so this says subatomic particles are real and have a measurable impact on the universe. Absolutely. Let me show you. So right there, that's Fermilab. They're the big shots. I'm in CERN. And I'm not an idiot at this either. Now, I went to the University of Geneva for particle physics, and I showed them all our stuff, and they had no denial of what I was doing. And as a matter of fact, they were impressed. And they actually did some of the stuff that I told them we were doing to the Large Hadron Collider. It shut down for 3 years, and they put in CMOS, which is what we use to visualize, and they put in focusing. And then they did some other general stuff too. It took 3 years. And now they're getting better results, but it's still nothing like we're getting. We're getting every single particle is creating this crushed field event. What they're doing is crushing fields head on. But instead, they think, I don't know what they think at this point, to be honest with you, because I showed them every little detail. And it's just no question, what I'm showing, it can be supported. It has to be looked into. they hit head on, and they just get a splash of stuff like this. We hit head on, and here's what we get. We get fission and fusion. All right, we hit head on. So here's the particles. That's ours. When we hit into the Venturi, which is here, it rips the black away from the white. You see that? That's fission. And the white goes into shower mode, and that's fusion. That's a sterile muon. That's electron showers. That's the holy grail of physics right now. We've done this long ago, and it's not hard to do. It's very easy to do. But you have to start with light. You can't start with these big, huge particles, because then you end up with just debris. All right, here's what they see. This is what they see. Well, what are you going to find with that? They do know that the blue particles, let me show you something. This is kind of interesting. This is Fermilab. What do you see there? Well, I can tell you what you see. Two huge graviton-like particles found in quantum. Well, I found them a long time ago. Graviton means they just hold each other together. Those are the black particles. Now, these come crashing together. So their ultimate goal is to make two particles hit head on. Well, you got two huge ones like this, at least this big. Boom, and when they do, stuff goes. Well, guess what? You got different colors. Why are the different colors? And why are the red ones all sort of stayed around here? And the blue ones and the yellow ones and the green ones took off and the white ones took off and never came back? It's because of how tightly they're held to the core. The red ones are held tightly, so they just sort of bounce around and flutter around on the outside. Here's what the actual, let me see, I got it up here somewhere. Here it is. This is what I believe is the actual proton and neutrons are built like this, which means they're nothing but little particles. So one proton is not a couple of quarks and this and that and a big ball like this so you can smash it up into like glass. No, it's a ball like this. And deep inside the center is where the black is. So it's always been in everything you look at here has dark matter in it, everything. You just can't see it because the only thing that bounces back is the light. The black is just an attractor. It never emits. It doesn't reflect. It doesn't do anything. It only attracts. And it's cold, completely, totally cold. That's the cold, dark matter. And these are the glowy hot matter. And that's the only two particles that make up anything is the white electron and the dark muon. These are neutrinos. And when you add them together, two of them together make what they call a gluon, which we would always thought of that as an electron. It's sort of, heat and so forth. But it's actually two poles in a electron. It's not just a negative. We always thought it was just that. No, none of this. But it's both. And that's the strong nuclear force, subatomic nuclear force. That's the tight part, very tight. Photons are two of these stacked back to back. When they're back to back like that, they're just like two bar magnets. That's all it is. And then there's a big magnetic field surrounding them. So anything they have to push through their magnetic field excites the other magnetic field, and they both glow a little bit. And this I will show you now. All right, this is red pulsed laser. Now, these are the gas particles in the air, and every one of them has a magnetic field. And as this accelerates into their field, it glows like crazy, and these also have to glow. Anytime you see glow, that's an increase in energy. That's an energetic reaction. It's like banging into a wall. Anytime you see glow, it's energy. All right, you see this? Remember the other shot I was just showing you? This particle accelerating, starting to accelerate and concussing with all the other magnetic fields, and that's why everything's glowing. It's just a big push. That's why you have a wave and you have a particle. Well, that's from Rod Warren. He's in Australia. And here's from his nephew, Dylan Carpenter, in New Zealand. And I lost touch with these guys several years ago, and I don't know, I can't really give you any extreme details other than this was taken with a cell phone. Dylan sent it to me. He said, what do you think? I said, whoa. What it is, these are the magnetic fields surrounding something spinning behind here. I don't know what, it's got to be a planet or spinning behind here. This is the moon. Now, all of these interacting fields are what they're looking for right now, gravity waves. All right, you see them? They're interacting fields. They're working with each other. Now, the moon does not have a field. It's plowing through space and not spinning. If it spins, it gets a field. If it doesn't spin, no field. All right, and I'm sure that the rate of spin affects the size of the field. The faster the spin, the tighter the field. Now, you can see it it's losing energy as it comes out, just like a magnet does. A magnet got a field out to here. You push it in, and you can feel them opposing each other, and then up here, it's nothing. The same thing here. Now, all of these are dipoles. You see it when you have a black and you have a white like that. That's a dipole, and this is a strange looking dipole. The black is much different than it normally is. Much, much different. But the white is, they glow white. They have a white and then a black. And it's a dipole. See that? Black and a white. And there's going to be a black over here. This is... and all of these are black and white. See? Black and white, black and white, black and white. Virtually everything is a dipole if it spins. All right, pay attention to this picture right here. This is red laser light. And particles of light are particles of light. Doesn't matter if from a laser, from a regular light bulb, from a candle. It's light, it's light. And it's supposed to go at a certain speed, and it's supposed to have this and that. Well, I don't think any of that stuff is correct. Now, what you're seeing is the spinning particles. You see it? Bzz, 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 bzz. You can see every one of those is literally a photon. Now, why is that glowing? Why is that glowing? And these here, they're not glowing like that. Well, I can tell you why. There's a bundle of fields together. You see them? There's a whole little package of fields, all sort of converging on the other partner's fields. And anytime you get interaction of field to field, you get a glow. That's what energy is. Energy is field to field. Energy is not E equals mc squared. That makes no sense whatsoever. Energy is related to a whole batch of other things. One is the density of what you started with. Secondly, how fast it's going. Thirdly, what it impacts with, because that's the only time you get the energy. Until it hits something, it's potential energy. It becomes kinetic energy, energy in actual motion when it bangs into something. All right, and you're going to bang into another field. They never really hit the particles. It's a field-to-field compression, and right in between the two fields, you get what's called a Casimir effect, and that's where the stuff gets real energetic, right in between the two fields. And that's what we're seeing right in here, right in between the fields. And when we put it through the Venturi, that's what we really call crushing the fields. And here's what the Venturi does. You see this? All right, pay attention to this now. Remember I showed you that wave coming through? We were somewhere back here before it started to really accelerate. It was starting to accelerate, and that's the only reason we could see it. This same wave is over in here and here and here. They're all over the place, and I can prove that because you can see them here. And I'll tell you why you can see them here, but you can't see them out here. They're all coming forward from that laser. Now, this one is being pulled forward. That's why you see it, because it's glowing anytime it's pushing harder than it should be. It glows more and more the harder and harder and harder it pushes. So we're starting to see it glow from basically total darkness. Then we see it actually accelerate the particle out of the wave and pull itself right out of its magnetic wave. And now at this point, it's going so fast that when it hits right about this point, it's concussing with its own backwards reverse electromotive force, they call it. Because what happens is when it hits the Venturi here, it can't get through. The black can't get through. The white can get squirt through, but still it bounces back. And when it bounces back, you see how this extreme amount of energetic reaction, that is just off the charts energy. That's energy off the charts. And what happens is right there, the photon shows up because it thinks it hit a wall. You don't get a photon until it bounces back. All right, and then you gotta get it back as light, whatever light it's going to be. But the photon itself, the nice little photon that looks basically like that. All right, and what it has is an upspin and a downspin. So this right here would be called a downspin. Whoops. Whoop, we just put it through the Venturi. And it all fell apart. When the glowy one is on the bottom, it's downspin. When the glowy one is at the top, all right, if we flip this over, if the glowy one was at the top and the other, you understand what I'm saying. One way is the downspin here. If this particle was up here, it would be the upspin. And then as it charges up, it flips. And I can actually show you all these things I'm talking about. I'm not just guessing. I can show you these things happening. That's that red laser, all right, accelerating. When it accelerates, it looks just like this. As I told you, you don't have photons until you get pretty good solid concussion. Out here, they're neutrinos. They get more and more and more and more energy. That's why they say a neutrino changes flavors. Well, it does, because it's getting more and more interaction with what's bouncing back at it. It's starting to compress more and more and more and more and more. And as it does, this is actually bouncing back. You see these white strips? They're smacking back at it. This photon right here thinks it hit a wall. It thinks it just hit a wall because of this reverse reaction. All right, and then it explodes into pieces over here. It breaks and does what's called fission and fusion. All right, so that was that particle coming. And the green is the same particle. You see this is the green here? And you see how we're going off in this direction. All right, why wouldn't that particle be this way here? Because it's going in this direction. They always go to the Earth. They always go to Earth ground. Polarized towards the Earth, because it's a dipole particle. It's a polarized particle, so it's going to be straight up and down towards the Earth. Same thing happens with the red one. This one is better. The green is better because you can see it's going off to the side, but it's still straight up and down. The red, we're showing it sort of coming straight across, but it is still straight up and down, and that's just the way they are. All right, now you see this one's down. This is upspin, they call it. It has the white up here. Well, as it moved forward, the white charged up and flipped to the back, and then the discharged one came to the front, and that will start to charge up, and then that one will flip, and it'll flip, and it'll flip. They call it the muon wobble. And the green one actually was right in the phase of getting ready to do that, I believe. You see it right there? It's just getting ready to flip. See, it's a downspin. And the downspin is now glowed up so much it's going to go rip, and then the white one will come in front and start to charge up, and then it'll go rip, and the white one. So that's your upspin, your downspin. That explains that one, I think. Now, I just want to make this statement, and it's quite obvious. If light has to pass through these fields and these particles that are in space, and these light particles that are in space and all the dust, the light is going to slow down. It's not going to continue at the same speed. Light slows down, it speeds up. I've shown this extremely clearly. It's fully understood. That means that the planets are not being pulled away so fast that they're pulling the light with them and stretching it to the red. It's just shifting slower and slower and slower, and getting the frequencies are getting longer and longer and longer. As they bang, they lose a little piece of their frequency. Bang the next time a little more. Bang the next time a little more. Bang the next time a little more. And eventually, they're going to slow down. They don't just go forever. Space is not a vacuum. It's absolutely 100% undeniable, unequivocally, certainly saturated with particles and things. The light coming through there isn't going to come through here just to have a nice time. I'm going as fast as I never slow down. Einstein, literally, with this law, has destroyed science, destroyed cosmology, destroyed everything, basically. The laws, these laws and constants are not good. They're not good at all because they're just not right. Just not right at all. And we accelerated light. We created fission and fusion. Here it is right here. These are the particles from Fermilab. I think we spoke about Fermilab. The same particles. And they have the same characteristics. The white one gets big and small. The black one never changes. At the Venturi, after we the acceleration happens because the Venturi is in the way. And they just start to accelerate. And that's what's happened here. And then at that point, it's just like a nozzle on a hose. You got a whole bunch of water coming down. You turn the nozzle down and psh, it goes real fast. It's virtually identical. And water is not much different than light. Light is the same basic, it's like a liquid of particles. That's just almost like a liquid. All right, I keep talking about a Venturi, and this is all a Venturi is you have light coming through here, which is just light particles coming down here. Well, all of a sudden we put this Venturi in the way down here. So the light has to crush itself down to get through that Venturi. So all we really did was put this in, just like this. All right, so it would be right there. Now, what happened is a little tiny pinch there, a tiny, tiny, tiny pinch. And the black particles can't get through. They get banged back out of there. They can't get through. And only the white sprays through there. That's 100% white. Now you can do it where you open that Venturi up a little more and you get some of both. So this is the 100% white right here. You see that? The black can't get through. They're all the same size particles. They never change size. These are the same size as every other black particle here. They're all identical. One size fits all. Now, you see them in different looks because you only can see them when they're sitting on top of the white. They're all over in here too. They're everywhere. The black is everywhere. But you only see it when it sits on top of the white. That's why we've never seen it, because everything we look at the light bounces back at us. We don't see anything behind the white, because the white bounces, the black just absorbs. That's why it's dark matter. But it's heavy. And everything there is composed of the white and the black, both. So that's why everything has mass and has weight to it. And the black can go right together and touch each other, couldn't care less. The white wants to get away. That's why it explodes here. The black, no problem. You see it over here? Right on top of each other. Couldn't care less. The white, as soon as they get close into here, they just go off like a firecracker. They hate each other. So the electron and neutrino, the white and the black come in here, and boom, when they hit the heavy water, the white showers, the black goes by itself. All right, blue laser is just rocket ship laser. Now here's coming in, and you see how close these little bands are? Those are the interference patterns. So it's a bang, boom, 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 bang, boom. And it's getting slower and slower and slower, stretching the wave. So here it's extremely blue on the blue end, almost into ultraviolet. But by the time it gets out to here, it's stretched out more. All right, and all it is a particle like this, spinning here. And it was real tight here, going bzzz, it comes out and it stretches down to here. Light speeds up, light slows down, no problem whatsoever. See, this is a different deal. The other one was light going through glass and making that mound in the middle. This is light going through the air, but that's the blue, very, very hot coming in here. And you can see it's almost going straight, and then it's spinning to the right, drifting to the left. And by the time you get out here, you can see that it's made of two particles. But the blue is very, very powerful. And this is basically like a jet fighter coming through the air, only in this case, I believe this is glass. And that mound is the energetic field of the spinning particle coming through here. And each one of these is a compression pop. And it just gets weaker and weaker and weaker as it goes out, that's all. And eventually it'll get stretched out until it's, it's going to be hard to see. That's why the further away you get from something, you lose the brightness. That's all. That's all this is. And you see this? All kinds of talk now about gravity waves. And you see that black ball? You see the white ball? It's a dipoles. And they're starting to show pictures. Wow, we think this one must look like this. But why don't you just look at my pictures? Because this is exactly what it does look like. All right, these are magnetic dipole field lines. And anything that spins in space, and that's why, motors, you spin them, and the fields interact with other fields. The two fields interact with the other fields, and it pushes the electricity out. It pushes the white particles into some collection device, battery or whatever. That's what a generator is. It generates by pushing field against field. These are field against field. Light is a particle that has a field. I mean, I've shown it. There's no question whatsoever. It's true. So, at this point, they don't realize even why global warming is happening. As I said, the global warming is happening because of the scrub of these particles into all of the extensive amount of particles that are in space. This is when it gets scrubby. Now, when the sun possibly hits some obstruction in front of it, it would get a solar flare, and it would have a cosmic ray, cosmic emission. All right, so let's say the sun is cruising around, spinning through space. All right, and one of these is the sun. Let's say that little ball right there is us. That's our sun, and we're spinning around, having a good time. Everybody's happy. And all of a sudden, bam, we hit some dense spot in space. And our sun says, whoa, and it just emits all of this radiation because it just got slapped. All right, now what would it get slapped with? I don't know. Would it be something huge that we could see? Maybe. Maybe we wouldn't see it. Maybe we wouldn't even have to see it. Maybe it would be a magnetic signature that would hit it. Some big heavy-duty magnet job. I mean, look at what's going on out here. Who the hell even knows? Nobody knows what that's about. There's nobody on Earth can explain that. You find me anybody that can explain any of this. Explain that to me. That looks like a pyramid to me, and it looks like they got a spacecraft going back and forth to something that looks like Atlantis. I don't know what to think. What do you think? This is the moon. What's this doing on top of the moon, or between us and the moon? What's this all about? And why is this blue on the leading edge of the moon? And I can tell you why. It's because it's the leading edge. It's moving through space this way, forward. And as the light hits it, it crushes the light from the normal spectrum here into the blue. All right. Normally, it would stretch it out into the red, they say, because everything's being pulled away. Well, when you go the other direction, it pushes light into the blue spectrum, and that's what's happening right there. So the moon is going this direction. It doesn't spin, though. These fields that you see impressed over the top of the moon are from something else. That is not the moon's fields. So we got a lot to think about, my friends. And, if they're going to make a big deal out of the solar eclipse, well, that's fine. But if you want to know why the corona is so hot, it's simply because it's scrubbing through these particles that are in space. And you can see it. It's probably somewhere right about out here is where the real serious corona takes effect, where these field lines reconverge, but I don't know. Now, the reason you see these three in these exact zones is because that is where the main impact is going to be out here. So that's going to be the reddest red. But then that is going to push a field away and push a field away this way. Then you're going to get another one down here and another one down here, because these are the major impact sites. And that's the field lines. Now, dipole electron flood theory solves virtually all of this stuff. And if anybody can come up with something, I'd like them to present it to me. Because, I mean, dark matter now is no problem. It sits right in the center of the white matter. Light accelerates. Light slows down. Light is a particle. Light has a field around it, so it creates a wave. Light can be split. We can keep the muon part away from the electron neutrino part. And if you do that, that is generation of electricity. That is generating electricity, is to separate the white from the black, which is exactly what we did in copious quantities. A total separation. You put a harvester right in there, like that, a solar panel, and collect that stuff. That's electricity. All it wants to do in its life is to get back to these black guys. As long as this can get back to that, it's going to be happy. And it'll go through a motor, it'll go through a heater, it'll go through anything. It'll go right through your body to get back to the dark matter. Because the Earth is gravity, and it's dark matter because it is more saturated with the dark than it is with the white. The Earth is an attractor. So it has to be more dense with the dark matter, because the dark matter is just an attractor. And it sucks the white down into it. So I hope this has been a bit of an eye-opener. I know I get a little carried away with this stuff, but if you don't get carried away, you don't even understand it. You're just not going to understand anything of it. You say, oh, I can understand that. Here's the green and the red going the same time through the same slit. Look at how, the green is just much more powerful than the red. Pushes the red right out of the way and keeps going this way. Remember I said they only spin going this way? Always pointed down to Mother Earth. Well, this is the one case you will never see this again. Right there. They're spinning this way. You see that? That is almost unheard of, because and the only reason it's doing it is because the green, being much more powerful than the red, has grabbed a hold of the red's field and spun it this way. All right? So as far as I'm concerned, the green looks to me like it's going faster than the red, because it like it pushed right past the red and made it spin this direction. That doesn't happen. You see that? I hope you can see that. You see the little spins they're doing? That's just unheard of. I've never seen that before, ever. The only time you see that is when the green is pushing the red out of the way. So the red is down here with this little four banger down there, like this, only it's red. And this comes back so fast that it grabs it and just spins it this way. Normally they spin around on their pole. This time it's going this way. Very, very unusual. All this stuff is unusual. All right, I'm going to just leave it at this. Dipole electron flood theory, which means that there is nothing more than the black and white particles tied together as dipoles, and they just build into protons, they become stable for some reason at approximately 1823 of these particles together. They become semi-stable. They're still charged. If they go to even number, 1824, it's neutral, because it doesn't want to take another one on or give one up. At an uneven number, it wants one more or wants to give one up. So I say dipole electron flood theory basically changes everything, because they know that the standard model doesn't work. It doesn't account for gravity. They can't find the dark matter. They don't understand why we're scrubbing through the universe. They think the universe is a vacuum. I showed you all this stuff. That's not a thing. Not one of those things is true. So it's time to at least examine this. I mean, this is not nothing. This is all. It's better than these little doodles. These are all real things I'm showing. The other ones are virtually all doodles, every one of them. So, dipole electron flood theory, my friends, that's the new solution to everything. And I think we can get free electricity. I think we can get free electricity and carry it around in little lunchbox. You see this? This is my concept of what we could do with this. You saw how that laser restricted and only allowed the white particles through. The white particles are what you need to run a car. You need to charge a battery. That's all we want is the white, and we can force them down into a battery or run it right away, and then we can use a portion of that to continue the laser. So it should be self-generating. You don't have to put any batteries in or anything, or you'd have to have some to kick it off, or maybe even a capacitor, but you'd have to have something to get it started. And once it's started, it should kick off enough juice to support the system. Now, if you had thousands of these lasers, which you could easily have inside of a box like this, you could have thousands. These are like the heads of a pin. And if it was engineered correctly, you could have them in banks of them, straight down, boom, 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 boom. Every one of them being a separate laser, every one of them being a separate Venturi, and then on the other side being one massive harvester that would collect it down. And then you could put it through whatever kind of outlet you want. You just click it over. I want AC, DC, whatever. All of that regulation, that's no problem. It's all done already. All we need to do is to be able to get electricity in there, which is this white juice. And if you have the white juice, you're good. If you have the black and white, that's nothing. That's no good. The black and white is just pressure. We need the white particle, which has no weight whatsoever, none, zero. Because when you charge up a battery, nothing changes. The battery just becomes more powerful. The white has no mass. And I will show you right now, one more time, in the nuclear bomb blast. You can see the white come up and burn the house, and then the black comes finally, and then the house goes down. The white never even makes the smoke move. I'll show you that. Okay, I am going to show you this bomb blast. All right, this is a nuclear test house. This is from a place called atomcentral.com on YouTube. And they show some of these tests. Now, what you're going to see is an extreme amount of glow, and then you just see everything smoke up. Even the wires, the poles, the roof, the curtains, the house, everything. Anything that is combustible, which means it can absorb electrons and burn, will burn, because what it's going to get is electrons, but they have no weight. Otherwise, it would push. I'm going to show you this. They have no weight. It's amazing. So I'm going to show you this, then I'm going to show you our experiments, and then we're going to come back to this again. So here it goes. They're going to shoot off this bomb, and I have it going very slow. And they move the truck out of the way and all that stuff. Boom, off it goes. Now, you see what it's doing? The bomb went off. Nothing's moving. Look at these poles. Look at the wires. Look at the roof. It's smoke. It's just coming up. It's not even moving. How could that possibly be? How could that be a nuclear bomb blast and nothing is even moving? The reason is the only things that have hit so far are the white outside particles, because they surround the dark core. Now the dark core is going to catch up with it, and when it does, then that's when the house goes. So here goes. It just keeps smoking, smoking, smoking. It's just now just smoking. That's it. It's almost done. Boom, here it comes. There it is right there. I just stopped it. Look at it. That's just like bowling balls coming at it now. Look at it. Boom. All right. So that shows you the difference between the white hitting it first, then the black hitting it. All right, I know you saw this before, and this is just nothing but white. Not one single black particle is getting through there. Zero. However, that Venturi, you can tune it in and out. And Rod Warren is the guy that knows how to do this. I can't do this. This takes hours and days and weeks and years, literally, to figure out how to do this, and he's done it. He's unbelievable. Now, coming through the Venturi this time, we've got both black and white. And what pushes? The black pushes the white. That's literally identical to what you saw in that nuclear explosion. Boom! Everything lit up. So here's the house. What happened next? Burn, 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 burn. It didn't go, it didn't move it anywhere. And then all of a sudden the black hits, there goes the house. All right, are you with me? Through the Venturi. So just say this is an atomic bomb. We have it going only in one direction because we've got it focused, which is it's kind of an interesting concept. But we got focused that atomic bomb, subatomic bomb, into this direction and push those white particles and burn that house up, and then the house goes. So as I showed you before, that's exactly what happens. And we're going to go back and see it again. All right, here it goes. The first thing goes off is just nothing but glow. And that's because it's nothing but the white particles. Boom, there it goes. Smoke, smoke, smoke. No movie, no movie. Smoky, smoky, smoky. No movie. Pew. Case closed for the house. Okay, so if I'm right, which quite obviously I am, the corona is being heated up because of its scrubbing. That's all it is. The same as our ionosphere, the same deal. And we don't really understand the global warming. But it is, I believe it's because the expansion of our atmosphere is making a balloon effect, and it's scrubbing harder and harder and harder. That's what I'm taking away from this. It could be that we're just entering a more dense area in space. I don't know. But something is causing more reaction here, because I know for a fact, I'm not going to pull up the article, but I did find an article about, and I think it was from Yale, but I'm not sure, that they found this layer here was getting cooler. And they couldn't account for that, and they made it sound like that means we're really not in that bad of a shape down here. No, that means that we're worse shape, because the cooler it gets here, the hotter it gets down here. I think I've made this pretty clear. Everything's dipoles. Hot, cold, hot. And then cold is the dark matter of Earth. So it's hot, cold, cold. The Earth itself is basically cold. And it'll suck electrons in. That's why. Anytime the electrons get sucked in, it's I don't know how to explain it, but the electrons getting sucked in is boy. Okay, my friends, I suppose I should leave it at this. This is the issue that we're dealing with. Is the corona is getting hotter. Is hot out there, millions of degrees, because the sun is scrubbing through the solar system just as we are. We're getting hotter out here, I believe hotter out here, and then hotter on the face of the Earth, because the expansion of our gases and our envelope and our atmosphere, which expands the ionosphere out harder and scrubs harder. And that also accounts for all the tumultuous, nasty stuff that's going on with the climate change. This is all due to climate change. This scrub causes a lot of turmoil. Just think about this. The more scrub out here, well, here, hold on. I got a little picture that I drew a while back here. All right, so here we got the Earth. The more scrub we have out here, so that first of all was scrubbing, everything was fine, everybody's having a good time. Hold on, let me turn the lights on. All right, everything's going good. And then all of a sudden we started burning oil, like just unbelievable amounts of oil and fossil fuel. It's all sequestered. It's all locked in solid conditions. Once you expand it, I mean, the expansion rate of this stuff is just astronomical. So here we had an atmosphere that was around here, somewhere around here. Now all of a sudden we got an atmosphere that's somewhere out here. That's what I'm thinking, because of that expansion of these gases. And it's not that the carbon can't get away. It's because the gases have electrons attached to them. And those electrons get stripped off in this outer region of the ionosphere. Negative ions are in the ionosphere, and they are also in the corona. it's dense with these particles of scrub. And that's where you just like scrubbing your tires down the road. It gets hotter and hotter and hotter. And we're plowing through who knows what. So there's no telling if it's plowing through something denser, or it's, in our case, I'm almost certain it's the expansion of our gaseous envelope, and that's creating all the hurricanes and floods and tornadoes and enormous amounts of hail, huge pieces of hail, because of that cold region getting colder. Remember I said the cold region, if it gets colder, it gets hotter on the Earth? Same thing. Out here, we have huge amounts of hail come down now, some of them boulder size, and they're coming out of a colder region here. So the hotter it gets here, the colder it gets here. The colder it gets here, the hotter it gets down here, and the more turmoil. And the Earth itself is cold and sucks electrons down to it. So it's just nothing more than layers of dipolarity. All right, I love you all. You know, the solar eclipse is interesting, but it would be much more interesting to understand our relationship to the global warming and all the things that are in space. And again, light doesn't not slow down. Light slows down, absolutely, no question. Coming through there, zero question. This is going to be altered from wherever that light is coming through. And if it's coming through from a blank space, it's going to not be altered as much. If it's coming through something like this, it's going to be slowed down a lot. All right, I love you all. Happy Easter.